just introduce our first speaker. Our first speaker is Marc Kaplan. He's the co-founder of VeryCloud and indeed a leading voice in the space of quantum internet. So a warm welcome. Thank you.
Good afternoon, everyone. So I'm here to talk about the effort, the worldwide effort, or the European effort, at least, to build a quantum internet. I won't really deep dive into quantum things, but talk more about the potential applications of this quantum internet, the motivations, where we are, and so on. But let's start with introducing, who we are at VeryCloud. We work on this topic for a number of years now to try to design quantum network applications, right? So we know how to build, as you will see, quantum networks. The question is, what are they good for? And these are a few of the deliverables that we obtained within a mostly research project called the Quantum Internet Alliance, led by the Technical University of Delft. So in particular, trying to match the theory of what can be done on quantum networks with potential use cases. This is this report in the middle. And one of the things that I strongly encourage you to look at if you're interested in the topic is this protocol library that we're hosting, and I will give the address at the end on how to reach it. Okay, so quantum networks, you can read the term in the literature, but it covers a lot of different potential instantiations. Depending on the technology that you have in your lab or in your company or to process quantum information, it corresponds to different type of networks that you can build, right? And there are some networks actually that we can build today, and some stages of quantum networks that are very much long term. So today, what we have is the first line here, quantum key distribution networks. They only require to prepare single qubits, send them through, let's say, an optical fiber, and measure them at the end. And if you were there this morning, you could see the experiment going on, run by Neverlocal here. And if you weren't there this morning, you can visit Neverlocal's booth and see how it works. So it's something that is possible to do, even at an industrial level. And then you have, so preparing those qubits is easy. Measuring these qubits are somewhat easy, as long as it's just one qubit at a time. These are things that we can do. However, beyond that, we don't know much for now, right? So repeating, this notion of repeaters is something that is very hard to achieve for quantum networks. So extending photons, optical fibers are lossy. You lose a lot of photons, half of them every 20 kilometers, if I remember well. So you need repeaters to extend the distance, and this is something that is very hard to build. When you can build entangled states, whatever that means, I won't go into the details here. You can also add them to your network. Quantum memories, quantum computers, these are the stages of quantum computing. And what is interesting for us, at VeryCloud and as people are interested in quantum information, is that each new stage here, you shouldn't wait until you have quantum computers to build quantum networks. Actually, you should start with current existing quantum networks and make them evolve. The reason is that each time you add some of the hardware here, you will also unlock new applications. And what I want to do today is to walk you through this, future history of quantum networks, showing you what is possible today and what are those applications that will get unlocked in the future. Some of them are really weird, by the way. Yeah? The goal is not to demystify quantum. Actually, quantum is mystical, and I will not try to hide that. Okay, so the only thing that is running today at industrial scale on quantum networks is quantum key distribution. I call it the mother of all protocols because although it was not the first quantum communication or the quantum information processing task, it's sort of the one that captures very naturally the properties of quantum systems and translates them into cybersecurity properties. So by sending these, quantum states one by one, something that we can do very, well, somewhat easily using photons, sending them from one party to another, Alice and Bob here can establish a key that is unconditionally secure. What is interesting is that it's something that is provably impossible with classical communication. So using these quantum systems, you can do something that is provably impossible with classical systems. And by unconditionally secure, what we mean here is that if an adversary, this property, this security derives from the fact that if an adversary tries to observe the communication that is happening, because of deep fundamental physics properties, he will change the states, and this you can observe, by running some statistics over what was happening. So it's possible to derive a full security proof showing that the key, the mutual information between the key that Alice and Bob share and the adversary is zero, after some post-processing. It's possible to achieve that. Quantum key distribution network, again, not only it's possible today, but it's also deployed at a somewhat industrial scale, I would say. In Europe, we have 27 national test beds running at the moment. Some countries even have several test beds running in parallel. In Asia, we are at a commercial stage, so it's very hard to know for real what is happening in China, but Singapore or Korea have commercial offers if you want to connect to their quantum key distribution networks. In the US, they have a slightly different approach. I don't know what's the justification for that, but they could build these networks if they wanted to. Interestingly, quantum key distribution exists. For us, it's very interesting when you start looking at it as a building block for further application. And one of the things that we do at VeriCloud is we have this application running on top of quantum key distribution networks that transfers the security of your communication and the fact that the key cannot be copied to the security of storage. So we can run distributed storage over several QKD networks, which corresponds exactly to the current situation. There is a small QKD network in Singapore, small QKD network in Canada, and so on, and we can use that to have provably, a security that is provably better than using a single QKD network or classical networks only. Okay, so the problem, if you remember my picture earlier, right? Quantum key distribution involves only two parties, Alice and Bob, of course. They want to establish a shared key, and this is what's happening. So when you want to scale it to a network and have several parties, this is an issue, right? How can you have end-to-end security when distributing keys over a network rather than just point-to-point? This is far from obvious. You need to have these repeaters to route the quantum information through the network. And at the moment, there are two potential solutions to this problem, but these are lab experiments. The first one is to distribute entanglement on the network, and the second one is to use quantum error correction. And they're both very, very hard to achieve. It's running, so entanglement distribution works in lab. It starts to be deployed in significant or relevant environment. At this stage of repeater network, there is also an interesting story that you can use quantum information to have more secure confidential computing, classical confidential computing. So you can run, so my example here is that you have Alice and Bob that try to establish the intersection of their tables, for example. And it turns out that you can prove that there is an advantage in terms of the security assumptions that you need to achieve this task on quantum networks compared to classical networks. Of course, it's a task that has numerous applications. I'm not going to oversell it and tell you that this is where quantum networks are relevant, but at least it's something that should be tested, and as far as I can tell, it has never been tested out of a research lab. And it requires exactly the same hardware as quantum key distribution. It's just that if you want to reach long distances, once again, you need these quantum repeaters that we don't know how to build today, or that we don't know how to build in a real environment. Okay, now let's get even weirder. Unclonable cryptography. Now, suppose now I have quantum memories. Quantum memories are devices that can receive the quantum states that are flowing through the network, can store them for an unlimited amount of time, and when I need, I can either release those quantum states and send them further to another party on the network, or measure them. So there's no processing in the memory. It just stores the state and sends them. It turns out that this stage, in my opinion, is one of the most interesting intermediate stages that we have in the building of these quantum networks, because it unlocks all these tasks that we usually put under the name of unclonable cryptography. So quantum money protocols, we'll hear about them more, I think tomorrow. Unclonable encryption, I can store some information on a server with a physical guarantee that the server cannot copy it on another server, so it cannot share my information. Certified deletion, I can ask the server to give me a mathematical proof that it has erased the data that I stored. This is very interesting, and interestingly, quantum memories now, there are a few startups that start commercializing quantum memories. So I believe that we'll see more and more experiments in the future. And by the way, even though there are startups, it's still very early work, and we're starting a project with NeverLocal to try to determine what are the parameters that we need for these quantum memories to show anything relevant for applying quantum money protocols in the blockchain environment. See, so this is how we relate to blockchain in general. We know that they could be useful, and it's worth investigating it, but it all starts with simulating and spending time to implement the protocols first on simulator and then hopefully on real hardware. Last but not least, this is of course, this is the killer app. This is the killer app for quantum networks, but also it's the furthest, because you need quantum computers. Once you have quantum computers, with the devices that we have today, the ones for quantum key distribution, you can run secure quantum cloud computing. What do I mean by quantum cloud computing is that these devices can send an encrypted version of the circuit, the quantum circuit, to be executed on a distant quantum computer. And by secure execution, what I mean is that the server remains blind, everything is encrypted, and it's also verifiable. By verifiable, what I mean is that the client can verify that the computation that the server is doing is the one that it has paid for. And this relates to very deep questions, again, in physics. It's related to fully homomorphic encryption, but also a little bit different. This is what I want to say here. We also participate in this type of, say, research problem here, and we showed that the hardware, by the way, yeah, we also manufacture hardware for quantum communication, and we showed that our hardware is well suited not only to run blind quantum computing, but also to scale it to a multi-user case. And although we didn't have a quantum computer, we could use mini quantum computers here at the University Sapienza in Rome. Okay, so in conclusion, quantum communication is today a mature technology. You can purchase hardware to do it, and we've seen it this morning, but it only runs a single application, which is quantum key distribution, or let's say there is very nice work in progress to try to push further in deploying more and more application in today's hardware. Designing use cases is super interesting, but it's also super hard. You need smart people to design. Even if you know what you can do on your quantum network, applying it to a use case requires a lot of work. And this long-term horizon, we know it's a killer app for quantum computing, that you can have privacy by design on quantum networks. It's this long-term that we call this quantum utopia. Thanks a lot. This is the address if you want to look at, and learn more about quantum communication protocols here. And I strongly encourage you to start here if you're interested in the topic. Thank you.